Hi, everyone. Thanks for tuning in. My name is Albert. My colleagues Anvar and Axel and I are going to present to you our project, the Misophonia Filter. So the presentation is structured as follows. First, I'm going to explain to you what misophonia is, why it matters, and what it has to do with machine learning. This will lead directly to the project description. My colleague Anvar will explain to you how we approach this problem. He will mainly talk about data collection and data processing. Axel will explain to you what machine learning technique we decided to use, how it works, and how it performed in the end. And I will round up the presentation by talking about the limitations and scope for improvement. Now, before I explain to you what misophonia is, I want to invite you all to imagine the following situation with me. You're spending the night at a hotel. You're spending the night at a hotel. You are tired. You're exhausted. It was a long day, and all you need at this moment is a good night rest. You go to bed, and sleep is finally settling over you. Until suddenly you hear the sound of a leaking faucet. You can hear the sounds very clearly, drop after drop. What is going on through your mind at this moment? While some of you might have fallen asleep right now, many others, I bet, I can assure you, will have a hard time falling asleep again because the sound suddenly gets louder and louder until you can't sleep or even think. Now, imagine this would happen with everyday sounds on a daily basis. And even further, the reaction you get is much stronger, resulting in rage, anxiety, or even panic. And then you get a slight idea of what a person with misophonia experiences every day. Here's the definition. Misophonia, literally meaning the hatred of sounds, is a term coined in 2000 and often referred to as the selective sound syndrome. It's a proposed neurological condition where particular sounds elicit a strong emotional response, such as hate, anger, anxiety, rage, panic, or even physiological distress. So what does it mean that it's proposed? It simply means it's not yet officially classified. It's fairly new, it's being researched, the criteria are not very clear yet. It's neurological. It means it's not just a hypersensitivity to sounds. It has a direct impact on the autonomous nervous system. It's like comparable to a poke in the rib. And what sounds are we talking about here? It might sound funny to you, but by far most common sounds are oral, such as eating, chewing, smacking, speaking with a dry mouth, swallowing. But in rare cases might also be the sound of a keyboard. And some of you might think now, is this for real? Does this sound really create such strong emotions? And for those, I want to show you a quick demonstration. Tasty, right? Tasty, not for me. Well, why talking about misophonia? Surprisingly, up to 20% of the population have some degree of misophonia. And obviously, it affects the lives of the people immensely. So basically, any situation involving food or eating can be very, very difficult for people with misophonia. So they start avoiding it, which results in other people being rejected, family, friends, colleagues. So it has a great, great, great impact. And I'm not talking about the moments that people can't escape. So just imagine being stuck in an elevator with someone with a chewing gum for even a minute. This is real torture. Now, what does this have to do with machine learning? Right now, unfortunately, there are no evidence-based methods for treatments. This is simply because it's very new and it's still being researched. But we believe that machine learning can not get rid of misophonia, but at least help people to be less exposed to these sounds. So we present to you our misophonia filter. The big idea here, the big picture is to help people in any situation that might be difficult to not be exposed to these sounds. So this could be a situation you watch a video online and you want to pre-process the video because is a speaker talking, has a dry mouth, the recording is bad, the microphone is too close. And you just want to be able to get the contents. So I, for instance, watched a lot of Andrew NG videos and I had a hard time listening to him. And though the content was really, really important, I couldn't. So use this pre-process and enjoy the contents. Or this could be, it could be something on your phone during a live conversation, or ideally something that you put in whenever you need it in everyday life. You want to cancel out all the difficult noises, but still listen to the input that you need to do whatever you want to do. How would this work? The very first step is to make a machine learn to classify these sounds. That means to make it understand, to make it distinguish videos or audio files that contain such disgusting sounds from videos that do not contain them. If that works, one can go a step further and teach the machine to exactly understand where such sound starts and when they end. When that works, you can precisely and effectively filter these sounds. And for the device in your ear, you would need something that predicts the sound in seconds or milliseconds in time in the future. So these are the three big steps. In our project, we are mainly showing you that the first step is doable, which is arguably the most important one here. And how we approach this, my colleague Anvar will explain to you.
Thank you, Albert, to nice introduction. On the next coming slides, I'm going to talk about, as you said, data collection and processing. So we, since we start with step one, which is classifying the data as containing SMEC sounds or not SMEC sounds, our goal here is to collect a lot of such a video or audio files. There are two approaches. One is label data manually. The second one is use different sources for positive and negative classes. So here the approach one. For approach one, we listen through a whole video or audio file, like a talk or a speech, and label the starting and the end of each SMEC sound as shown on the slide. And then we cut this audio file into slices of a fixed length, like a half second. So as a result, we have two classes of slices. One contains the starting or the ending of the SMEC sound, or the both were labeled as 1. The rest of the slices labeled as 0. This approach is very precise and model allow to train a model to predict whether or not there is a SMEC sound, but also where it is exactly. This is very significant for predicting SMEC sound. But there is a big disadvantage of this approach, which is the process is very, very time consuming. Now we discuss the second approach, which is the first of all, we choose ASMR videos, as we watched above, where people create discussing sounds and slice them up, and simply each slice labeled as 1. For the negative samples, any kind of video containing speech can be taken, but no single SMEC sound. The As I said, this approach for this approach, two classes of samples or two classes of samples are taken from two different sources. The great advantage of this approach is that we have created a lot of or big data in a short amount of time. Uh, However, there is a disadvantage here, which is the recording quality of the sound in ASMR videos, as you have watched it, is so specific. To minimize this problem, we applied data augmentation. On the slide, you may see change pitch, shift in time, or noise injection. At the top, you see the original data. After the data augmentation is applied, the data on the bottom has been obtained. Yeah. So finally, we have a data, but how the information can be extracted? First of all, audio files are stored as a series of numbers where each number denotes the amplitude at a given moment of time. Secondly, this series of numbers can create some a curve like here in a time domain, which contains or sum of multiple sine functions. On the slide, you can see the curve contains or sum of two sine functions. These functions represents underlying frequency of the audio file. How this frequency can be extracted? Here, the mathematical transformation, which is called as the Fourier transformation, comes to help us. After the transformation shows us peaks here for each frequency. On the next slide, even more complicated mathematical transformation allows us to transform or converting the audio file to such a picture, which is called as a Mel spectrogram. Here, the brighter color corresponds to higher amplitude. The x-axis represents the time, y-axis represents the frequency in the logarithmic scale. How the data can be extracted from such a beautiful picture, it will be explained by Axel.
Sure. Thank you, Anvar. So to recap, we chop up our audio files into tiny, tiny little pieces, and then we convert them into images, into visual representations known as Mel spectrograms, like this one behind me. So let's see an example. So this is a little piece of audio. We can see the raw audio on top and the Mel spectrogram, the visual representation below. And there is a smack sound here inside the yellow rectangle. So let's see if we can actually play this
categories onto different types of people. So this is unsupervised learning. Categories onto different types of people. So this is unsupervised learning.
So what we need to do now is build a model that can detect this yellow little rectangle or what's inside of it. And what's interesting here is that we are using visual representations of the sounds. So our audio problem has now become a visual problem. It has become a computer vision problem. So we're just going to use a very simple traditional computer vision technique called convolutional neural network. And a few people have already talked about that, but basically it just means sliding a filter over your image and looking for certain shapes or patterns in the image. So that gives you an output like the green square here, where it's like a map of the different shapes and patterns, so we can see where in the image they occur. So that is what a CNN is, a convolutional neural network, and we just connect that to the output layer. That's it. It's a very, very simple model. So, and when I say output layer, it's actually just like an output neuron. like just one single neuron giving us 1 or 0, smack or no smack. So let's see how this model trained. We can see the loss curve on top. It's looking pretty good, if you ask me. No crazy overfitting, at least. And below it, we can see the accuracy curve, which is looking fine as well. We're reaching 97% validation accuracy. So basically, if we feed the model a sound, it can, with 97% accuracy, predict if it is a smack sound or not a smack sound. However, this only applies to our data set, which means there are some limitations for real-world use, which I think Albert can cover in more detail.
Yeah, I have to take over this sad part. As you rightly said, like in all data science problems, the results are strictly linked to the data use. So whatever you want the machine to learn, you have to show the machine this data. And we've fed the neural network only with the so-called ASMR videos that you heard at the beginning, very loud, special recording, specifically done for people who like this, actually. Funny side note. Since this was our only way to get a lot of data at once, we worked with it. And we have to deal with the problem that our network is not yet able to predict, given this training predicts sounds in a very different recording, like the one we heard earlier from Andrew NG, where the sound appears in between speech and is much shorter and maybe not as loud and as clear. Sorry, yeah, that's obviously one limitation. Another one worth mentioning is that for the task of predicting the sound in advance, there actually has to be cues in the sound itself that the machine can pick up. So, for example, a sound like the one from Andrew again, there's a pattern in the sounds. Often people make a pause, they swallow, they smack, and then they start talking again. So there's a pattern here that could be picked up by a machine. However, many, many other sounds are way more diverse, and we as humans are not able to predict the sounds. And until we know what a machine can do, we are not yet sure. Luckily, machines do outperform humans in audio, but we are yet to see whether this is the case here as well. Ultimately, I still want to end on a positive note, because what we've shown here is that the machine is able to pick up a lot of different sounds. And what we need to do now is to feed it with way more sounds recorded in way more different ways. And we're likely to see much better results on new data. Also, with a lot more time given, we can go back to the previous labeling system, which was the manual labeling. So give the exact start and the exact end of each smack sounds. And then we can expect a much higher accuracy. And also, most importantly, we would be able to build something like a YouTube filter that you can apply and can cancel out these sounds precisely as it should, precisely where they appear. And ultimately, with a lot more data, another chance would be to create multiple classes, so people the machine can distinguish between different disgusting sounds, and people can have a more customized filtering experience based on their particular needs. Yeah, so I think that's it from us. Thank you very much for listening. And if you have any questions, feel free to ask now, or write me an email, or find me on LinkedIn. Here you have the details. Thank you very much.